Assalamu alaikum. My name is Sayyida Abida Zahra, roll number 21TE111, Lab 5, Representation of Discrete Time Digital Signals into Frequency Domain. Lab Objectives: Representation of discrete time digital signals into frequency domain, resolution of spectrum, computation of magnitude, phase, and power spectrum, spectrum leaking and avoiding spectrum leaking. Now moving towards the task 1. The MATLAB code implements the discrete Fourier transform DFT and its inverse IDFT using two functions, myDFT and myIDFT. Both functions perform element-wise calculations, which can be inefficient for large datasets due to repeated multiplication and exponentiation. MyDFT function takes a signal x of length n as input, initializes an empty array y of the same size to store the DFT coefficients. MyIDFT takes the DFT coefficients y of length n as input, initializes an empty array x of the same size to store the reconstructed signal, divides x n plus 1 by n to normalize the inverse DFT, returns the recommended reconstructed signal x, and display in the output. So here is the output 1, DFT coefficients, IDFT sequence, output 2, DFT coefficients, IDFT sequence, output 3, DFT coefficients, IDFT sequence, and output 4 with DFT coefficients and IDFT sequence. Now task 2. The code defines 10 vectors x1 to x11 with varying lengths and contents, potentially representing different signals. It then plots the magnitude spectrum of the ninth signal x9 using the stem function and adds a title. Stem ABS FFT x9. This line plots the magnitude spectrum using the stem function, where each stem represents the magnitude of a frequency component. Title x9n minus 32. This line adds a title to the plot indicating that it shows the magnitude spectrum of x9 with a length of 32. Here is the output. Now moving towards the task 3. The code starts by defining a signal x as a vector of 4 numbers 1, 2, 3, 4. The FFTX function calculates the DFT of x. The real x and IMAG x functions extract the real and imaginary parts of the DFT coefficients. The ABSX function calculates the magnitude. The output for XMAG shows the correct magnitudes. So task 4. The code demonstrates how to analyze discrete time signals using the fast Fourier transform, which decomposes a signal into its constituent frequency components, defines 11 signal sequences x1 to x11 with varying lengths, values, and padding, calculates the FFTs of each signal using FFTX, storing the results in variables x1 to x11, extracts the magnitude, phase, and power components from the complex FFT coefficients. Magnitude x mag is equals to mag is equals to absx. Phase x phase is equals to angle x. Power x power is equals to x mag raised to power 2. Creates a figure with 3 subplots: magnitude spectrum, phase spectrum, and power spectrum. Magnitude spectrum plots the magnitude of x5 using stem. Phase spectrum plots the phase of x5 using stem. And the power spectrum plots the power of x5 using stem. Here are the three subplots in the output. First is the magnitude spectrum of x5, second is the phase spectrum of x5, and the third is power spectrum of x5.